Hi everyone, welcome to math. Welcome to Time for Math, because it's time for some math. So today we want to talk about zeros and ones, using binary digits to express things. Okay, so zeros and ones. One thing we can do with zeros and ones is represent the subsets of a set. And also, it's like Gödel coding. So, Gödel had the idea that takes anything and turn it into numbers. And if you can take something like a word and you can find a code for that word in numbers, then you can turn those numbers into binary, into just zeros and ones. So we're gonna speaking like computers. So maybe our vocabulary is very limited, but we can explain everything if we just talk long enough. Okay. So it's a good way to operate. Okay, so let's look at this set, a 3-element set. This set here, and I didn't say explicitly last time, but I talked about the number 3 and how it has cardinality 3. Any set that can be put into a one-to-one correspondence with 3 has cardinality 3. So this set, we can count it also, it's pretty clear, right? But the official definition of what it means to have cardinality 3 means that there's a one-to-one correspondence between your set and the number 3. Okay. So let's look at all the subsets of this set, or in other words, the power set of this set. So here's the set S. And we want to know, what about the power set? Okay, so I'm going to draw it. Okay, so I guess today we're talking about the power set of a set, which is the set of all subsets. So you can just think of a subset as a smaller version, or it could be the same size. It could be the same exact set. That's the max it can be. Anywhere from nothing to all the elements of the set. Okay, and all those included in between, in the extremes. Okay, so we want to represent each subset with binary numbers, with zeros and ones. So I know the empty set is a subset of every set. Something is a subset, A is a subset of B if every element of A is an element of B. And is it true? Is every element of the empty set an element of every set? Yeah, the empty set's a subset of every set, vacuously, because it doesn't have any elements. So yeah, it passes the hypothesis. Every element of the empty set, yeah, it doesn't have any elements. Okay, so the empty set will represent, we'll say 0 means you're out. And 1 means you're in the subset. Okay. So 0, 0, 0 represents the empty set. And it says there's no elements in this set. And if we draw a picture, it's just nothing. Maybe not even draw like that. Okay, then let's say the other extreme would be the subset that contains all the elements of the original set. Okay, and so these are always in every power set, these two extremes. And we can use the binary numbers to sort of organize our process for writing down all the subsets. So I've got all the extremes, and now I'm going to do all the one element subsets. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so let's keep track. That's 5 already. I'm missing some still, and I don't have room, so I have to erase this. Okay. So that's 5 so far. Let's keep track. Okay, we did all the one element subsets and we did the extremes, the whole set, and the empty set. So now let's do the 2 element subsets. So I can do these two, the triangle and the circle. I can do the square and the circle. And that's it. Okay. So we got a total of 8 subsets. And we can think of, why is it 8? You can think of the multiplication principle. At each stage, you're going to each element and you're deciding, is it in or out? So there's 2 choices, there's 2 options here. We can make a binary tree that goes with it. Even without labeling the tree, we can still like look at the process of what's going on. I guess we could label a little bit. Okay, so we could say, I better be like a little bit careful. Okay, I'm gonna have to erase this. So let's see what's going on. So think of this as like a decision tree when we're saying we're making subsets. And here I'm going to decide about the square. So first so our set is here. Square, triangle, circle. So our set is here, and here we're saying, hey buddy, is the square going to be in or out? Okay. You can think of, actually maybe I should just write it at this level. Say it like this. This is the level of the choice about the square. Okay, and we're going to write both worlds, both things that could happen. Yeah, we think of it like it's a little easier to think of it like I'm making choices, you know, like you're God or something, and you're deciding what's in this subset or this set, so you can see the whole picture. Okay, and so think of it like a decision tree. Okay, so this is a square in or out. Okay, so I start with nothing. So I will write some labels here. So I start with nothing. Okay, but maybe we just don't think about the root. Okay, so what do I do? Well, okay, so I can just stay with nothing. And then, okay, on the right, we'll decide to add the square. Okay, I can tell this is gonna run out of room if I draw it like this, so let me. Okay, I'm gonna dismiss the label from the root, just start with the root. Okay, and then to the left, we'll do nothing. And to the right, we'll do something. In this level, we're thinking about, should I add the square? Okay, now I make... So here we added a square, and we should keep track. Okay. Now, same thing. To the left, I keep doing nothing. To the right, I do something. And now this time at this level, I'm thinking about the triangle. Should I add the triangle or not? To the right, I will add the triangle to whatever is already there. So we're always building off of this node here. Okay, this one, I already have a square. So I'm going to do square and triangle here. Oh, I'm not going to do anything. To the left, I don't do anything. To the right, I add the level in question. So square, triangle. And then we have one more decision to make, and that's about the circle. Okay, now it's getting a little messy, so I'm going to replace these with binary numbers. Okay, and let's just keep track. We're going to say the first level is the square, the next level is the triangle, and then the circle. Okay, so you might think this is the ordering: square, triangle, circle, as far as like what subset it is. Okay, so I'll call this one 1, 0, 0. We'll call this 0, 0, 0. And then to the left, 1, 0, 0. And to the right, 1, 1, 0. And this is 0, 0, 0, 0, 1, 0. This is 0, 0, 0. Okay, so it's kind of like leftmost digit. Okay. Okay, and now we're making the decision about adding the circle. Okay, so I'm going to do nothing. And then the circle is the last digit, so 0, 0, 1. Okay, this one I'm deciding whether to make this digit a 1 or a 0. So to the left I don't change it, to the right I do change it. To the left I don't do anything. To the right I make the digit on the right a 1. Here I don't do anything on the left, and I make the farthest right digit a 1. Okay, so now I can see every subset as a branch through the tree. So this is the empty set. This is the set that just contains the circle, because I kept this in this order. So it's like you're writing a code, and as long as you keep track of the levels of what your code means, what the digits, how the digits correspond with the levels, then you can go back and see which subset goes with which branch. Okay, this is the one that's just the triangle. This is the one that has the triangle and the circle. This is the one that has just the square. This is the one that has the square and the circle. This is the one that has the square and the triangle. And this is the one that has all three. And so let's see, 1, 2, 3, 4, 5, 6, 7, 8, right? Because it's like a decision. So we're using the multiplication principle. So the first decision, I have two choices to make. Add the square to the subset or not. And then from each of those decisions, I make another decision. Should I add the triangle or not? So that's another factor of 2. And then from each of those worlds already, I make another choice to add the circle or not. And so that's another decision with 2 outcomes. Okay, so we multiply our choices at each level and we get 8. So that's all for today, and I hope you have a great day, and see you next time on Time for Math.